This is a short video about 6.3.1. It's Pollard's p-1 method, and it's a way to try to factor large integers. And it serves as like the motivation for the elliptic curve factorization method that will be in the next section of Stein's number theory book here. So the first thing we need to get comfortable with is what is this definition 6.3.1 about power smooth. So if you have a positive integer b, and if n is a positive number whose prime factorization is this product of these powers of pi, so pi to the ei, we're going to say that n is b power smooth if each prime power, pi to the ei, is at most b for each I. And equivalently, that b is bigger than or equal to just the largest prime power, pi to the ei, in that factorization. And so to give you an alternative example to the book over on the side, 72, it's 2 cubed times 3 squared. 72 is going to be b power smooth for any b larger than the largest prime power that we see in the factorization. So for any b that's bigger than or equal to 9, 72 would be b power smooth. And again, that 9 is 3 squared, which is the largest, pi to the ei, the largest prime power in the factorization of 72. So just how we use this word, right? 72, it's 9 power smooth, it's 10 power smooth, it's 11 power smooth, etc. So the first thing that we're going to do in Sage is write out or an algorithm that would actually compute what's the least common multiple of the first b integers. And that's going to help us with some b power smooth computations a little bit later on. And in Sage, if I'm scrolling to page 130 here, it's just this highlighted thing in light green here. Focus on that. So the LCM up to b. So again, it'll compute the least common multiple of all the integers up to b, all the positive integers up to b. And it's a little bit faster than kind of the naive algorithm, which is capital LCM. So we'll use this lowercase LCM up to. Now, what are we going to do? Let's get into what is Pollard's p-1 method, and you'll see how this b power smooth is actually used in that. So what we're going to try to do is, again, the goal here is you've got some integer capital N, and you want to factor it. And we're happy if we just obtain one of its prime factors, because then we can divide and make the number smaller, right? So we really just want to get our hands on one factor of n. And remember, like an RSA, like that's all you need. You just need one factor and then the whole scheme is broken. So same idea here. We're kind of still under the impression that factoring integers in general is a hard problem when they're very large. So finding one of the factors is kind of the key. So let's suppose that there is a prime divisor p of n such that p-1 is a b power smooth number, where b is just some positive integer picked ahead of time, and in practice you would probably change what this b is, and just it's kind of a hunt and peck. And so anyway, that's kind of a big assumption, and I'll talk about that a little bit later too. So, we're assuming that such a prime exists, and assuming such a prime exists, what we're going to talk about is how would you find that prime? In no way am I saying that there should exist such a prime, right? We're just going to say, if there is one, here's how you'd find it. So again, you're not necessarily going to find such a prime every single time, and that's why Pollard's p-1 method, it only works some of the time. But again, some of the times maybe better than none of the time. So how does this work? So we're going to look for a prime divisor p of n such that p-1 is b power smooth. And again, assuming one exists, here's how we would go about doing that. So again, on the other side here, I'm just reiterating, that's important because if you can find that prime p, well then you've got a factor of n, therefore you could factor the rest of n as well by dividing. So what do we know? If a is bigger than 1 and it's not divisible by p, then I know that a to the p-1 power is congruent to 1 mod p. And you should recall that. That's a form of Euler's theorem, and more generally, Euler's theorem says that a to the phi of n is congruent to 1 mod n, whenever a and n are relatively prime. That's what I mean by GCD of a and n is equal to 1 over there. So what we're going to do is we're going to let little m here denote the least common multiple of all the integers up to this b that has been picked out ahead of time. And like in a homework problem, say you'd be given what b is to play with. But again, in practice, you're probably going to change what b is and see if the following algorithm works or not, depending on what b is. So what are we going to do? M is going to be the least common multiple of all the integers up to b. So I'm here in this blue part, and observe here that, by the green assumption there that p-1 is b power smooth, that tells me that p-1 has to divide m, this least common multiple of all these integers up to b. And the reason for that's pretty simple. p-1 has this factorization, q1 to the e1, blah, 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 qm to the em, where again, I'm assuming the q's are primes, so these are just what are the prime powers in the factorization of p-1. Well, each one of those prime powers is less than or equal to b for each I. So in other words, each one of those prime powers, qi, it appears in this list of numbers 1, 2, 3 up to b. So when I take the least common multiple, right, the qi's to the ei's are going to be numbers that are in that product, in that least common multiple computation. So in other words, right, each qi to the ei has to divide this least common multiple. Therefore, each one has to divide m, and so therefore p minus 1 itself has to divide m as well. So in other words, right, if each one of these individually divides m, then so does their product. In other words, p minus 1 has to divide m. So hope you followed along with that. And so what else do I know then? Well, if a to the p minus 1 was congruent to 1 mod p, well then a to a power divisible by p minus 1 should also be congruent to 1 mod p. And just to make sure that we all follow that okay, if p minus 1 divides m, well then m is equal to p minus 1 times some integer k. And then now what I'll do is just think about exponent rules. I could do a to the p minus 1 power first, which is 1, and I'm just raising that to the k. So that just justifies what's going on in yellow here. And so what do we know then? P has to divide the greatest common divisor of a to the m minus 1 and n. And so where does, oops, sorry, I went a little too far. Where does this a to the m minus 1 come from? That's here. That's this yellow statement just translated. Saying that a to the m is congruent to 1 mod p is the same thing as saying that p divides the difference of a to the m and 1. Now, just to say a few more words about this over here, why is this true? What we've done is, so far, if I zoom out a little bit, in the green up there, I have assumed that p divides capital N, and what we've just got done showing is that p also divides a to the m minus 1. Therefore, this prime p has to divide the GCD of a to the m minus 1 and n. And the other thing that we know is we've got a prime divisor of the GCD, therefore the GCD can't be 1, right? Since the GCD has to be divisible by a prime, and 1 certainly is not. All right, so then that is our goal here. That's not our goal, that's what's going on. So you've got your GCD. If the GCD is a number that's strictly less than n, well, then that's a non-trivial factor of n, and we're done. So the computer's found it for us, or we'll have Sage find it for us in a minute. Now, like, what are the kind of the edge cases, or maybe not edge cases, but what could go wrong? Well, we're not guaranteed that GCD is going to be less than n. So it could be bad if it's actually equal to n itself, right? What if n also divides a to the m minus 1? Well, in that case, what we'll try to do is we're going to repeat the above steps, but again, we're going to adjust what b is perhaps. And this is where I've said we're kind of guessing and checking. So in problems, in a controlled environment like a class, you're given a b, but like in practice, you might have to change your choice of b. And what else you might do is you might also change your choice of a. Remember up here, a was just any number that was relatively prime to p. So you might tweak b or a. And the last thing to do, or really as the book says, maybe it should be the first thing that you do, is just to make sure that n itself is not a perfect power of m to the r. So it's not the power of like a single integer. All right, and so algorithm 6.3.4 is kind of a formalization of how we would go about trying to implement Pollard's method. And in the next part, on page 131, there's a lot of examples that illustrate how that method works by hand if you're interested. And when I say by hand, like, not letting a computer algorithm actually do it. So like using a calculator to go through the steps. You can look at that if you're interested. Otherwise though, we're gonna skip right down to the Sage code, which is down here in purple. And so this purple is the Sage code that implements Pollard's method.